Welcome to the third video of the ongoing series Turning AI Gears Your Way. I'm the Tech Emissary, and today we'll discuss Alpha Beta Pruning, essentially a sequel to the Minimax algorithm that we discussed previously, since we faced a big problem, as you may recall, before, that we cannot possibly spare time for big trees with a huge number of nodes. So without further ado, let's dive right into it. So the first point is abundantly clear. You see a solution to this problem that we have described before in the title, which is Alpha Beta Pruning. Just a little joke I inserted there. And Minimax, as you may know, we already said it before. This is because that it cannot possibly get so much nodes in such efficient time, which is why we want to make it more efficient with this Alpha Beta Pruning. And the principle of this Alpha Beta Pruning is that it uses iterative deepening search, or IDS, as compared to breadth first search. Now, I'm going to be talking more about the benefits and what these two really are if you are not really sure about it yet, but this is going to be in the next video, so stay tuned for that. I'm going to be discussing it before we go on to our project in the fifth video. So eventually, with Alpha Beta Pruning, we can just move on to the necessary parts. We can just cut off what we don't need. It can just use its algorithm to be able to know which one to prune, as you may call it, which is seen in the picture on the top right corner. Essentially, that picture describes what is being happening. So basically, you're cutting off what is not needed that way, and you're able to know which one is going to be the next nodes that we're going to take and which ones can be thrown away. And essentially, I think that the best way to explain this is to be able to dive into another example directly, as I'm going to show you next. So this is an example of a typical tree that can be part of the alpha pruning action, beta pruning action. So basically, alpha beta pruning has two values, alpha and beta. Alpha is basically the best choice for value for max, while beta is the best choice for minimum, which is going to be, of course, the lowest value, opposing alpha. Each node can track their own alpha and beta values. So we will start alpha with going from minus infinity and beta from positive infinity. So we can see that when it's max turn, they'll want something to be greater than previous alpha but smaller than the previous or equal to beta, since we want beta alpha to be something that will go for the littlest possible values. On the other hand, min is going to try to keep beta at the minimum beta, but going to be smaller and greater than alpha. So basically, this will keep iterating until we are able to find one value that will keep being updated through the nodes. So for example, let's have our tree over here. Let's have our tree populated. So now, let's take this example. We can see that all the nodes here are already labeled with a number. So let's use this example for our purposes. So we can start from A and move along to B, where we'll do our first search, since that's the first tree it'll come across. So then eventually it'll come to the first node, 2. So as soon as you find that, we have B saying that it can't be anything greater than 2, so B has a bound that is equal to 2. So we move on to the next node, which is 19, but we see that that is not smaller than 2, so we can skip that. And we go to 9. Again, when we compare with 2, it's not smaller than 2. So we can just move that along to A eventually. And so our condition is now that if something wants to be replaced 2, it has to be greater than 2 or equal to. But equal to is just the same, so we won't take that either. So eventually we do the search in the next tree, which is C. So we see that the first node is 6, as you can see over there. So we will first raise that up. So now it has that limit. Now, as you can see there, we have 12, but it's not going to be bigger. It's not going to be less than 6. So it doesn't really matter equally, because essentially it's already much bigger. And eventually, because of that, we're just going to cut it. We don't need, because we are already seeing that 6 is basically the minimal amount here. And it won't matter if we look into the other trees. So essentially, we won't actually open 12 or 14. So essentially, we will just cross them out before we even look into them. So then we move on to the next tree, the third tree, which is D. So we have a few digits here. essentially we see 6, 7, and 9. So we see over here that, again, we can raise up 6 as the boundary for D. But again, since that's the minimal amount, and it won't really matter if we look into the others, so we can cross that out as well. Now, what you're seeing here is only a couple of nodes, but just imagine the possibilities you can save if you actually decide to prune these nodes, because there can be an entire tree down there. There can be maybe 6 layers down there. You may not even know it. So that's why it's essential to use alpha beta pruning to save time and costs in some cases. And this is very efficient. Of course, not all alpha beta pruning are ideal. For example, let's change the third node. We can see over there that, for example, we have nodes 6, 9, and 3. Now, we can't prune because we can see that the numbers are not ordered, basically. We can see that there's 6, 9, and 3. Eventually 3 can come up there. And that's the problem. So we can't always do alpha beta pruning. So basically, as you can see, the worst possible scenario that we can have in a alpha beta pruning situation is that if no pruning happens. On the other hand, the ideal situation we want is to have a lot of pruning to happen, because this can solve the tree much faster. And we have the perfect ordering formula, which is the order b to the power of m divided by 2. And b here is the branching factor, while m is the maximum apply depth. Further from there, we have bounding. So basically, this helps us to emphasize even more on efficiency. Basically, we use bounding with the we call cutoff search. So we also replace the utility with evaluation functions to be able to estimate the value of configurations on our playing board or field. And eventually, we use the idea of heuristics and domain knowledge to be able to emphasize all that. So that brings us to the end of the third video. I hope that you've been able to gain a lot of knowledge here. It's going to be essential for us when we do the project on video 5. In the next video, I'm going to be talking about what I said we will discuss before, including iterative deepening search, uniform cost search, breadth cost search, depth first search, and depth limited search. So this will clear up a lot of things that I've said along the way that may have not made a lot of sense to you. So we'll clear them up here. So I'll see you all in the next video. Thank you.